have everything recorded. Yep, so the bar is green, mic is working, so we can just go ahead and focus on the concepts. Okay, so this is the number circle. When you see the 4-digit numbers, those are all in binary. So we have 0, 0, 0, 0 right here, and then we increase the value until we get to 1, 1, 1, 1, which is the last value you can represent using only 4 bits. If I just give you 4 slots, okay, where each slot can be a 1 or a 0, you only got 16 ways or 16 things you can represent. Is that okay? All right. So now the question is, if I want to look at each one as a value, as an integer, okay, what is each bit pattern representing? That is the next question. So 0, 0, 0, 0 is pretty easy, right? Because it just looks like 0. In any other base, it is just 0. 0, 0, 0, 1, we get that one too, it's just 1. 0, 0, 1, 0 is representing what we know as 2, because as a binary number, the digit 0 tells us how many 2 to the power of zeros we have, which is 1, right? We have 0 of 1s. Digit 1 tells us how many 2 to the power of 1s do we have, which is 2. We got 1, 2 in this case. This is 4, this is 8, and we got none of those 2. So that means this entire thing is just representing the value of 2. So that's base conversion stuff that we have talked about some time ago. Okay? So everything looks okay and pretty easy to understand all the way up to 0, 1, 1, 1. So 0, 1, 1, 1 is no 8, 1, 4, 1, 2, 1, 1. They add up to 7. Okay? So it's representing 7. So we can say 8, 9, so on. It's fine. There's no problem with interpreting only using the non-negative integers. But then we have a problem, because if we can only represent non-negative values in a computer, then what do we do with our national deficit? Right? Or your student loan, which you may not have yet. But once you transfer, some of you may end up with a little bit of student loan. So we do have to deal with negative numbers at some point. So we cannot just say, oh, we can only represent non-negative values. Sometimes we have to represent negative values. So now the question is, well, what would be the natural representation of -1? Okay? Now there are several ways, and people look at it slightly differently. Because you can look at this as 0, 0, 0, 1 is representing just 1. Why don't we use the most significant bit, or the leftmost one? If it is a 1, then you interpret the rest as a negative number. If not, it is non-negative. Well, that's one way to look at it. But that interpretation has 2 problems. The first problem is we end up with 2 zeros. Because now you have a positive 0 and you have a negative 0. And some of you will say, but there's no such thing as a negative 0, because 0 is just 0. Yes, that's the whole point. We don't want to use 2 representations to represent the same thing, which is just 0. Okay? But that's a minor problem, because when you have a 32-bit number, you have 4 billion something representations. Losing just one of them is not a big deal. The second problem is more significant. How do we carry out computations when we represent negative values using that method? Can we still use the adder to add? Can we still use the subtractor to subtract both mechanisms that we have talked about up to this point? The answer was no. Okay? So if you use just 1 bit, okay, to represent the sign of the value, but maintain and use the same interpretation for the rest of the bits, it turns out to be very unfriendly to what we have already gone over for adding and subtracting. Okay? Now, what do I mean by that? Okay? Well, let's take a look at some binary subtraction and binary addition, but using the interpretation that is already in here. Okay? In particularly, we look at the red numbers, okay, the red values, and see if our adder, as it is, our subtractor, as it is, can handle this type of representation of negative values. So we'll go check it out. Okay, so I'm going to start up a notepad, or we use one that is already up and running, if I can find it. Nope, I cannot find it, so we'll start a new one. Okay, start a mouse pad. All right, so we'll go ahead and pick a particular example that involves a negative number. Okay, well, let's do something that's kind of obvious. Okay, we want to add 1 to -1. What should we end up with? We should end up with 0. Okay, so we have 0, 0, 0, 0, 0, 1 representing 1. And then we're going to add the representation of -1 to it. So if you just look up the number wheel, what bit pattern is representing -1? 1, 1, 1, 1. Okay, so we say 1, 1, 1, 1. And at this point, we are no longer looking at the actual value being represented. We're only looking at the bits at this point. So since this is not a chained addition from another addition, so that's why your K0 is assumed to be 0. All right, so now is a good time to test whether you guys still remember the stuff about binary addition. So what is the result of 1 plus 1? Okay, and the result of 0 plus 1? Okay, and this is another one. So should I have a 1 over here? Yes, because we have a 1 plus 1 of the top row. Okay, let me point out where. Here and here. So this is a 1. And do I have a 1 over here? Yes, because this 1 plus this 1 has a carry of 1. And the same situation over here. And we have an overall carry of 1. So now we can look at the sum row. 0 plus 0 is a 0. 1 plus 1 is a 0. 1 plus 1 is a 0. 1 plus 1 is a 0. Now when I say 1 plus 1 is a 0, I mean the result of 1 plus 1 is a 0, not counting the carry. Okay, so the carry is an entirely different thing in the way that we represent addition. So yeah, see? 1 plus -1 is 0. It all works out in a very strange way, right? What about that overall carry over here? We just ignore that, okay? Because when you are talking about a 4-bit by 4-bit addition, the result has to limit to only 4 bits. Is that okay? All right. So that works out, and some people may say, but Tech, you intentionally picked one example that is going to work out. Let's pick something that may not work out. So I'll let you guys pick, well, let's do a subtraction this time. So do a subtraction that involves at least one negative value, but the result has to be representable on the number wheel as well. Okay, so that's one kind of super duper restriction, and we'll get to that restriction a lot later on in this class. Not this particular lecture, but later on in additional topics. Say that one more time. -4 minus 2. Okay, very good. So -4 is represented by 1, 1, 0, 0, right? So I'll say this is representing -4. And you want to minus how much from it? 2. So 0, 0, 1, 0. Okay, so this is now a subtraction. And when we carry out the subtraction, we are only going to look at these operations as bitwise operations, as if we are just the logic gates doing the same work. Okay? And we assume this is a 0. The result of 0 minus 0, the R function, gives you a 0. This gives you a 1, this gives you a 1, this gives you a 1, because those are exclusive ORs. Okay? So now we look at this one and go like, should I end up with a 1 over here? Now remember, the borrow function is the negation of the first number, the minuend, and the non-negative version of the subtrahend, which is the second number. Okay? So in this case, not 0 is a 1, but this is a 0. So the conjunction would end up with a 0. And the same situation here. So neither this 0 minus this 0, nor this 0 minus this 0 is going to give me a borrow of 1. So that means I don't have a borrow of 1. Okay? So that means this is going to be a 0. So, sorry? Exactly. So this one does have a borrow because we have 0 minus 1 over here. 0 is the minuend, 1 is the subtrahend. So the way we compute the borrow is negating the minuend and the non-negative version of the subtrahend. In this case, not 0 is a 1, 1 and 1 is a 1. So we do have at least one subtraction yielding a borrow of 1. So we have a 1 over here. What about this one? We don't have a borrow, okay? Because 1 minus 0 does not have a borrow of 1. 1 minus 1 does not have a borrow of 1 either. So when you OR 0, 0, you end up with just a 0, okay? So you can see how this method is kind of awkward because you can work out one row at a time. You don't have to work by columns. You can just work the entire row first, okay? 0 minus 0 is a 0. This is just exclusive OR. 1 minus 0 is a 1. 1 minus 1 is a 0. 1 minus 1 is a 1. So according to the bitwise operations that we have just performed, -4 minus 2 will give us a bit pattern of 1, 0, 1, 0. So you look up the number wheel, okay? You look up 1, 0, 1, 0, and it does represent -6. So it works out again. So this is what I mean by we can use the same adder and the same subtractor as we talked about before. Okay, which is great, which means I don't have to waste silicon to have a specialized adder and a specialized subtractor just for signed integers. Signed or not, all integers would use the same adder and the same subtractor. It makes no difference whatsoever as far as the adder or the subtractor is concerned. Is that okay? Yep.
Saying like for the first example, if we have 1 plus -1, the -1 is represented as 15. The answer will still be 0, 0, 0, but it has that carry 1.
So the representation of what it is representing is kind of up to you, right? So this is representing 1, and in our calculation, we were looking at the interpretation of -1. Okay? So in that case, it works out because the answer is representing the value of 0. So in the second case, I'm just going to put the interpretation in parentheses just so that we know what we are dealing with here. So this is the representation of -6. So we can see how it is working out just fine. Okay? So, but this is interesting because it also kind of jives with something that I said on Tuesday. Okay, remember on Tuesday, I was asking you guys a question of, okay, should we look at this as signed or should we look at this as unsigned? And then I said, why do you care? Because the adder doesn't care, the subtractor doesn't care, right? It works in both cases. So the only time it matters is when you need to compare. Okay, so let me give you an actual concrete example out here. Okay, so if I want to say, okay, a certain memory location has 0, 0, 1, 0 in it, and I want to find out, okay, the question mark is asking, is it really less than, okay? And the other bit pattern is 1, 1, 0, 1, okay? It doesn't really matter what the other bits are, but I'm just going to use a concrete example here. So you retrieve the content of one location. It says, okay, I have the bit pattern of 0, 0, 1, 0. Another location says, I have the bit pattern of 1, 1, 0, 1. And your program in C, okay, is comparing, okay? If blah, blah, blah is less than blah, 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 do this, else do something else, okay? So you need to make a decision. So now you have to say, which way should I look at it? Because in this case, you can be asking whether 2 is less than 1101 is -3, or you can be asking whether 2 is less than 13. Because 1101 can be interpreted two ways. If you want to look at 1101 as a signed integer, it is -3. It represents -3. If you want to look at 1101 as an unsigned representation of an integer, then it'll be representing 13. And then it matters, because if you say it is signed, then it will go to the else case. If you look at it as unsigned, it will go to the then case in a conditional statement. It will go to two different branches, depending on whether it should be signed or unsigned. So comparison is the only time that it matters. Is that okay so far? Do we understand what that means? Okay, good. All right, so shall we move on? Yep, go ahead.
So when we set 0, 0, 0 as the numerical place for 0,
Mm-hmm.
logically it gives a definition of where 0 is and how to differentiate positive and negative value.
So are you referring back to the signed representation that we did not want to use?
Right, because I'm struggling with why does in binary are signed values always with the math that we're using, why is it always true?
Why is it always true? What do you mean by it is always true? What is always true?
Sorry. So we did an example of -4 minus 2.
Mm-hmm.
I'm looking at the values of 110 minus 001. I'm asking, how do we know that it always works?
Oh, okay. Why does it always work? Okay, so first of all, the way it works is, remember how we derived the R function and how we derived the B function for borrowing, for subtraction? So that is why it works, because all we did was to look at multi-digit addition and multi-digit subtraction, and then we know how base 10 works, right? Base 10 has a really complex R and B function, but binary-wise, it's super easy. And then we found out that if you want to look at the R function, it's the same thing as exclusive OR. Okay, you can do it with a single gate. If you want to look at the borrow function, yeah, that looks a little awkward because you have to negate the first one and then you AND the second one, right? But nonetheless, it can be done using Boolean operators, which means it can translate into logic gates. Remember that? That is why it works. Okay? The mysterious part is, why does it work with signed interpretation? Why does it work with negative values, right? Okay, so that's a legitimate question. Yes?
So if we're doing signed notation with this,
Mm-hmm.
are you going to be able to get to, if you're using signed notation,
Mm-hmm.
is 1111 going to be 15 or -1, or is it only going to be -1? Like, is that like USB0 thing?
Okay, so, all right.
You get only around
So let's take a step back first, okay? Because what are you doing with that 1111?
say comparison.
Hmm?
Say doing like a comparison. Like,
Okay, so you're comparing 1111 with something else, right? So in that case, you do need to know. You can only choose one interpretation. You cannot say, oh, okay, it can be 15 or -1. You have to choose one interpretation. You either choose and say that, okay, I'm only dealing with unsigned values, so it's going to be 15. Or you can say, I'm dealing with signed values, so it's -1. You cannot, so at that point, you have to choose. So when you look at a C program, the type of the variable would indicate whether it's signed or unsigned when you compare a variable with another variable.
okay. So if you are dealing with signed numbers and you needed to get, say, a 14, you just have to append two sevens together.
If you're using unsigned interpretation, right?
Sign.
If you're using signed interpretation, you cannot represent 14 anymore using 4 bits.
Okay, that was my question.
Yeah. And there was yeah, go ahead.
How would you represent negative numbers past -8?
You cannot. So you do have a certain range of values that you can represent given a fixed number of bits. Okay? So those are all very good questions. So the question now is, given n bits, okay, what is the range, oops, you guys cannot see that anymore, range of values in signed and in unsigned interpretations. Okay, so if you look at the number wheel to your left-hand side as an example, how would you generalize? You know, if I just say, okay, I give you n bits, okay? The example that I gave you has exactly 4 bits, so n equals to 4, but I want you to give me the range of values. What is the least value you can represent in signed interpretation? Yes?
N over 2.
N over 2? No. N is the number of bits. 2 to the power of n. You're getting minus 1. Thank you. So it is, so I don't know which way you want me to use, because I can use the caret symbol to mean to the power of, or I can just spell out the function, 2 to the power of n minus 1. And the negation of that, arithmetic negation of that, is the least value you can represent given that you have n bits. Okay? What is the largest value you can represent when you only have n bits and we are talking about the signed interpretation?
Power 2 to the n minus 1,
Uh-huh.
quantity minus 1.
The whole thing minus 1. Yep, exactly. So we have power 2n minus 1, then the whole thing minus 1. Oh. Huh? Oh, you cannot see. Oh, okay. All right, so let me see. I can still move this a little bit to the left. Then I can move this one over for a little bit. There we go. Now, this minus 1 is really important because in the case when n equals to 4, that means the largest value you can represent using the signed interpretation is 7. So the range of value you can represent goes from negative 8 to positive 7. And then somebody is going to say, that is so asymmetric. I mean, one is 8 and the other one is 7. It doesn't make sense. It makes perfect sense because 0 is taking up one place as a non-negative integer. Is that okay? So we have 8 negative integers from negative 1 down to negative 8, and then we have 8 non-negative integers from 0 to 7. It is perfectly symmetric, 8 versus 8. Is that okay? Now, not only that, okay, for now we just want to see it as an observation, okay? We are not going to explain it too much yet. If you look at all the values from negative 8 to negative 1, what is common to all of those 8 negative values, or the bit patterns representing negative values? What is common? Yes? They all start with 1. So the most significant bit, okay, which is this one, 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 and this one, is also known as the sign bit. Because by only looking at that one bit, okay, if you tell me that we are looking at the bits as signed interpretation, and I can only see that most significant bit, I can tell right away, is it representing something that's negative or something that is non-negative? And that's why it is called the sign bit. Okay? So the sign bit and the most significant bit, or the leftmost bit, are basically the same thing. Are we good so far? All right? Yep.
Like looking at numbers like in binary,
Mm-hmm.
you'd have to have someone else to note that it is either signed or unsigned, correct?
The most significant bit is what we use.
Okay. Well, I mean, but 1111 is 15 if it's unsigned and -1 if it's signed. So I'm assuming you just need something else to tell you whether it's a signed or an unsigned number.
Your code is going to do that. So when we talk about comparison, we'll start to look into what we call flags. So different flags are used to indicate the outcome of a comparison. So the comparison mechanism is still the same. Comparison is basically just subtraction, which is the same no matter whether it is signed versus unsigned. So that part doesn't change. but it will change different kinds of flags, which we haven't talked about yet. So if you say, I want to look at this as an unsigned comparison, we look at that flag. If you want to look at it as a signed, okay, the other one, okay, I cannot remember whether it was unsigned to begin with, but if you want to look at it, if you want to look at it as the other interpretation, then we look at a different flag to indicate the ordering. So that's something that we will talk about, but so far we have not yet touched the flags. We have touched it a little bit, but not a whole lot. Okay, so we'll try to finish this. What about the unsigned interpretation? In other words, we just look at all the letters in black, okay? In terms of the range of values. What is the smallest value we can represent using the unsigned interpretation? That's it. Yeah, okay, 0. Very good. So what is the highest or largest value we can represent looking at the bit patterns as unsigned interpretation? Power 2 to the power of n, the whole thing minus 1. Yep. So when n equals to 4, it goes from 0 to 15. Are we doing okay so far with the range of values given a certain number of bits? So it's basically just a trade-off, okay? If you want to include negative values in what you want to represent, you're shifting the entire range so that 0 is more or less at the center. If you want to look at, if you say, oh, I don't need to represent negative values, I want to have more non-negative values, you're shifting the whole range so that 0 is the far left of that range. That's it. You're just shifting the range. But the number of values you can represent does not change. You still only have 2 to the power of n representations. Yep.
Does changing the bit position of what represents 0 change the arithmetic?
No. And that's the beauty of looking at signed interpretation this way, is we don't need special adders nor special subtractors. Yep.
This might be a dumb question, but
There are no dumb questions
if we can change
because it's dumber not to ask. Okay, sorry for interrupting. Go ahead.
you can have signed integers, do
Uh-huh.
you even need a subtractor?
Yes, you do.
Why?
Because, so let's say our national debt is a certain number, right? And then today we have this many trade. Okay, we sold this much to other countries and we bought this much from other countries. So we need to update the national deficit, right? Then you need to either add or subtract, right? You're still adding, but whether you're adding a non-negative number or a negative number, that depends on the trade of that day. So you still need to use an adder or subtractor.
You can just add.
The negative version of something?
Yeah.
Well, yes, you can. So that's a good lead into the next topic. But the idea is we already have a subtractor.
Why not?
Why not? Exactly. So there are two things kind of going on in my head right now, which is very typical of me, more than one thread at the same time. So I'm going to pursue both of them if I remember both. The first one is, do you guys remember the P and the G terms in the carry or the borrow look ahead thing? What is the only difference between adding and subtracting when we define P and G? Whether x is negated or not, right? If we're subtracting, x is negated. If we are not subtracting, if we're adding, then x is non-negated. Before the and for G, and then before the or for P, right? Okay, so I want to show you a circuit in Logisim that will basically say, oh, once you have the basic carry log ahead adder done, you can easily turn it into a subtractor. You can turn it into a programmable circuit. So sometimes it subtracts, other times it adds. Okay, so that's one thing I want to go over. Okay, so let's do that first. Because it is a good way to demonstrate how to use Logisim in this case. All right. Uh-oh, where did it put it? Where did it go? Nope, it did not go at all. Oh, that's because, there we go. All right, so what we'll do is I will do a little bit of the circuitry that you guys have to deal with. Okay, this is x, one is x and one is y. So we'll label this one as x, and we'll label this one as y, just so that we can relate this to the terms that we have already talked about. And then on the other side, we have P and G. So in this circuit, P and G are output pins because that's the whole point. Okay, we just want to compute P and G, and then we have one extra input pin to specify: well, are we adding or are we subtracting? Okay, so we're going to label this one where I'm just trying to remember which one is which one. So 1 is going to be subtraction and 0 is going to be addition. Okay, so since so subtraction versus addition. Okay, so the way to read something like this is if it is a 1, it is for subtraction. If it is a 0, it is for addition. Okay. All right. And these are all X, Y, PG are supposed to be multi-bit input pins or multi-bit pins. So we'll make it 3 and 3. And the same thing for P and G. So we'll label this one as G. It is a 3-bit thing. And then this is G. Oh, this is P. And it's also a 3-bit thing. There we go. So hopefully we already know that we can just use a multi-bit OR for P and a multi-bit AND for G. Okay, so I'm hoping you guys already have gone through that exercise and already have that circuit in your code. I mean in your diagram. So we just go to the gate here. We pull an AND gate and say, let's change the size, change the number of inputs. Okay. And also change the number of data bits so that it matches, right? So the output is just like this, okay? Cool. And then we do an OR gate, same thing. Make it smaller, change the number of input to 2, and then change each input to 3-bit wide. And this one is going to go to P. Okay. So in an adder, okay, it's easy because we just have X going to the of the AND gate, going to the first pin of the OR gate, Y goes to the second pin of both gates, and we're done, right? But to use it as a subtractor, what we would have, if without the programmable bit over here, to turn the whole circuit into a subtractor, all you really have to do is to do this and this. Okay, now it becomes a subtractor. But then you go like, well, but that means we still have to rebuild the entire circuit because if this one is not compatible with the other one. So we don't want to do it this way. Undo. Okay? So what we want to do is we take X and then we take this particular bit over here and say, how can we have this bit to specify to negate X first before feeding into both of the AND or the OR gate or not? Okay, what was it? Say it one more time. Slash? A latch. Nope, you don't need a latch. You need exclusive OR. Okay, so let's see how exclusive OR is going to help. Okay, what is 0 exclusive OR with 0? That's just 0. Okay, what is 0 exclusive OR with 1? 1. Oh, so that's kind of negating the 0, right? Let's see whether it works the other way around. What is 1 exclusive OR with 0? It's still 1. It's not negated, right? What is 1 exclusive OR with 1? 0. Oh, so that means if the control line, which I label as sub/add, if this is what I exclusive OR with every bit of X, the result of that can now be fed into the AND and also the OR gate, so that I can say, then what I use the P and G for, would be either addition or subtraction. Okay, is that okay? I mean, do you guys kind of understand what I'm saying? More or less? Okay, let me finish this first, okay? You will see it. Okay, so what I need now is an exclusive OR gate. Okay, I go to gate, pull a exclusive OR. Do the same thing. We need a narrow version, 3-bit wide, and only 2 inputs, okay? And what we will do is, we'll take everything from X, okay, feed it into one of these, and then we'll also take this and feed it into the other one. And do you think what's going to happen here? It's going to complain because the subtract add control line only has 1 bit. But the gate, the exclusive OR gate, is saying, I want 3 bits in every single input. We have a problem. So what do we do to fix this problem? A splitter, very good. Okay, except this time we are not using a splitter to split. More like a replicator, because we are just replicating the same bit multiple times. So we take a splitter, we flip it, okay, so that the facing is opposite. And then we also need a 3x3, okay, because we have 3 bits to merge, okay. Okay, so we'll take this, extend this out a little bit, and take this wire, put it over here. So now this end is fine, right? Because the merged end of the splitter has 3 bits in that one single wire, okay? So that's all good. Now the question is, what do we do with this end? There's only 1 bit here, and then this is 1 bit, this is 1 bit, this is another bit. Have them all hooked up to the same thing. Now it's all good. As I said, it's not a merger, it's a replicator, because it's replicating the control line twice. So now we have 3 copies of the original thing, okay? So now the question is, but what is this really doing? Okay, what is happening to this wire? This is one great thing about LogicSim is you can play with it, okay? And nothing bad is going to happen except maybe crashing LogicSim itself. Okay, I have to remind people, many times in the semester of, okay, if you think that this may work, okay, if you have an idea of how to do something, do it. Nothing bad is going to happen. Nothing is going to explode. No one's going to die because of what you did. Okay, so go ahead and do it and see what happens, because that's one way for people to learn, is to experiment, find out, okay, this works the way that I thought it would, or it does not work the way that I thought it would. Either way, it's good. Yep.
Can't you change that into the fan in bit 1 and then both bit without the 3 bits?
Yeah, you can, well, you don't need, no, it cannot split, because this is 1 single bit already. You cannot split 1 bit into multiple bits. So a splitter cannot be used in place of this fork. The fork is basically saying it is really the same electrical connection, but it's connecting to bit 0, 1, and 2 of the merger. Okay? All right. So at this point, we'll do some experiments, okay? In other words, I'm turning into the poking tool, and I want to ask you, if I poke this wire right now, what should I see? Should I see 0, 0, 0, or should I see 1, 1, 1? I should see, okay, what is 0 exclusive OR with 0? 0. And I just did it like 3 times, right? And they're all zeros. Okay, cool. Okay, so let's put something more interesting here. This is 0, 1, 1. If I poke it here, what should I see? 0, 1, 1, non-negated, right? So let's double check. Yep, that really is the case. Cool. Now, let's flip the control line, okay? The control line is the one that is labeled sub/add, okay? We flip this one, okay? Now, what should I see? 1, 0, 0, because the exclusive OR is now acting as a NOT gate because we are exclusive ORing with 1. Okay? So let's double check. Come on. There we go. Do you see how one control line that I label as sub/add is now controlling whether X is negated first or not? Now, the Y is not connected yet to the gates, okay? But that's really just the last step, okay? I just have to go back to the selection tool, finish the wiring, like so. And then Y is non-negated either way, so we just have to, connect Y to both of the input pins as is. Now you have your P and G and also the control line. Now, where do you think the P and the G's are going to go if this were just a subpart of a circuit? They go to your K1, K2, K3. But don't we have to change the K1, K2, K3 depending on whether it's adding or subtracting? Well, just the label, right? I mean, because K is carry for adding and T is for subtracting. But that's just a label. The structure inside K1, K2, and K3 does not change. So we can reuse the most complicated part of the carry look-ahead or the borrow look-ahead mechanism. And this part is super easy to do in silicon because we are just doing the same thing to all the bits. Just, hey, whatever bit is coming in, flip it or not to flip it. Is that okay? So I just want to mention this, because this really connects to your homework assignment. You do not need to do a subtractor, okay? But in case, for those of you who want to say, oh, I want to turn this into a subtractor, this is all you need to do. Add one control line, okay? Add a merger, add a exclusive OR gate, and you're done. Are we doing okay so far with this? Okay, cool. So it's a slight digression from our main topic, but nonetheless, it is kind of important because the discussion was if we can represent signed values, do we still need subtraction? Well, subtraction is almost free to begin with. So did that answer your question? Kind of? Okay. Okay, but if you really want to get rid of a subtractor, because now we can represent negative values, don't you think we need a way to negate a value, like to turn a 3 into a negative 3? Because if you want to get rid of subtraction, then you have to say, okay, we need to negate this one first before we add this one to the other one in order to do what we normally do as a subtraction, right? Okay, so instead of saying it, I can just write it out and go like, okay. So we can say 3 minus 2 is really the same thing as 3 plus the negation of 2. Is that kind of what you were mentioning? Okay. So that means we need a mechanism to do this. We need a mechanism that will take the representation of 2 and then turn it into the representation of negative 2. Do we agree that that's kind of something that we need? Okay. So now I can just explain how to do that in 15 seconds. But you already know that that's not what I'm going to do, right? We'll take the scenic route. Life is short, okay? Why go to the destination in a hurry? Take the scenic route. Okay, so taking the scenic route means we have to go back and look at the number wheel. And then we say, well, this is 2, and this is what is representing negative 2. This is 3. This is what is representing negative 3. It doesn't seem like we have some quick and easy way to handle it, okay? So looking at the symmetry of the number wheel between the left-hand side and the right-hand side doesn't seem to work. Okay, fine, give it up. But we also notice something else. If you look at 15 and negative 1, and you say, what is 15 minus negative 1? That's 16. 14 minus negative 2, 16. 13 minus negative 3, that's 16. So we do notice there is a pattern over there. Is that okay? Okay. So we look at that pattern and go like, So that means, okay, so to express it here, okay, we notice the pattern of 15 minus negative 1 is 16, 14 minus negative 2 is also 16. 13 minus negative 3 is also 16, and so on. Okay, and the last entry is 8 minus negative 8 is also 16. Okay, but how is that going to help me? Because my objective is to look at the representation of 2 and then somehow turn it into the representation of negative 2. Right? Are we good so far? Okay? So then we say, let's single out this guy, okay? Because let's just focus on 2. So we'll do some algebra here. So we say this is negative 2, and then we do the 16 minus the 14 on the other side, okay? Nope, we have to do a negation on this side here. Yes? Okay, that seems to work. And we already know that this is 2. Okay. Okay. But so far we haven't really accomplished anything, right? I mean, this is just going back to square one. It just says negative 2 is negative 2, or negative 2 is the same as the arithmetic negation of 2, which we already know and it's not helping in any way. Okay, so we need to kind of look at this in a slightly different way then. Okay, so can we look at negative 2 as the negation? Okay, so we look at the negation of 16 minus 14 first. So we look at this, and okay, let me think about this. Okay, I just lost my train of thought. I have to kind of catch the train again. Okay. Now 16, okay, is 16 one of the values we can represent using only 4 bits, signed or unsigned? Nope. Okay, that's kind of a bummer. Okay. So when we look at the negation of 2, oh, okay, I remember what to do now. So we have 16 minus 16 minus 2. Does anyone want to challenge that negative 2 is not 16 minus 16 minus 2? Okay, that's pretty obvious, right? Okay, except 16 cannot be represented. Okay, so we look at this in a slightly different way. So we'll keep the 16 on the outside, and then we group these 2 first, and then have a minus 16 on the outside. Would that work? Okay, that's just algebra. I'm just moving things around a little bit. And then we look at this and go like, but we cannot represent 16 at all. Well, what is 16? Can we look at 16 as 15 plus 1? Okay. So we got 15 plus 1 minus 2, the whole thing minus 16. Is that okay? Huh? Okay. Well, hold on. There's more. So can we look at this as 15 minus 2 first, and then the plus 1, and then the whole thing minus 16? Yeah, I hope so. Yes? Okay. Now here comes the fun part. Can we look at this as bitwise not of 2 plus 1? And then the whole thing plus 16. Minus 16, sorry. There we go. This is the jump, okay? This is the one conceptual jump that takes a little bit of processing. Because in base 10, it doesn't make sense. But in base 2, it's like, yeah, we can do that. Why? Okay, I like that question. Why? Okay. So now the question is why, in fact, what we are asking, okay, let me pull over here. 15 minus 2 is bitwise not of 2 in 4-bit operations. But why? Well, what is the binary representation of 15 as a 4-bit number? You can, well, okay, so I'll let you cheat a little bit here. There you go. 1, 1, 1, 1. Okay, very good. Okay. So we got 1, 1, 1, 1. And what is the binary representation of 2? 0, 0, 1, 0, right? Okay. Do you think I need any additional columns just to do this subtraction? Do we need the borrow row to do this subtraction? There's no borrow. Now, how do you know there's absolutely no borrow in this subtraction? How is that guaranteed? Because the top row are all ones. Now, if the top row are all ones, it doesn't matter what the second row has, okay? Because 1 minus whatever has no borrow. Okay? So, now let's take a look at the actual outcome, okay? What is 1 minus 0? 1. 1 minus 1? 1 minus 0? 1. 1 minus 1, 0? It's also a 1. Oh, but isn't that just the arithmetic? Isn't that just the bitwise knot of the bit pattern of 0, 0, 1, 0? So now the question is, does it work in general? Okay, we know that it works when we are dealing with 2, but does it work in general? Okay, so what we want to do is now we are looking at something more like this. Okay, we have 1, 1, 1, 1. And then here we have, y3, y2, y1, and y0. Those are representing individual bits. Okay, so what do we have as the third row? Well, this is really just 1 minus y0, right? Yes. And this is just 1 minus y1, and so on. Okay, but the question is 1 minus y1 really the same thing as the bitwise knot of y1? Okay, let me reformulate the question because that's the essence. Okay, can we say 1 minus x is really just the bitwise knot of x, assuming x is just 1 bit? Okay, x is 1 single bit. What do you think? How do we prove it? Okay, let's just say that yes, it is. Okay, how do you prove it? See, this is what I refer to at the beginning of the semester as I'm not teaching you the knowledge, I'm teaching you the attitude to gain knowledge. Okay, is asking why. Okay, don't just write it down because tech says it, because tech says a lot of things, and some of those can be wrong. So you have to have an independent process in your head of asking, why does it work? How can I prove it to myself that it works? So how would you do it? Yes? Truth table, very good. This is why we like binary stuff or Boolean stuff, because you can use a truth table to prove a lot of things. Not everything, but a lot of things. So we have the truth table having 1 column for x because x is the only variable in this case. We have 1 minus x as 1 column, and then we have bitwise knot of x as the other column. Now, in this case, bitwise knot is really the same thing as logical knot because it is a single bit. Okay? Well, x is a binary digit. It can be 0, and then it can be 1. Can it be 2? No, because it's a binary digit. Okay? A binary digit can only be 0 or 1. It's the same thing as a Boolean. Okay? It can either be false or true, but there's no third value it can assume. Okay, fine. What is 1 minus 0? Regardless of the base. Just 1. What is 1 minus 1? 0. Okay. What is bitwise knot of 0 when we're only dealing with 1 bit? Okay. And what is bitwise knot of 1? Logical knot, 1 and 0. Okay. Do you see how 1 minus x and the bitwise they have identical values for every single row. That's it. That's your proof right there. Okay? This is your proof that 1 minus x as an arithmetic operation when x is a single bit is really doing exactly the same thing as bitwise not of x. Is that okay? All right? All right. So now that we got this little mystery solved, okay, we look at this whole chain of reasoning. We went from here to here. Okay? Then we still have this minus 16 on the outside to deal with. What am I going to deal with that? Well, let me ask you this question. We'll go back to the picture, which is here. Okay? Tell me what happens. Okay, we'll have a concrete example. We'll start with 3. Okay? And we'll do a subtract 16 by moving the hand 16 times in the negative direction. Okay? So the negative direction is counterclockwise, right? Okay? So we start with 3, and then we'll move the hand counterclockwise 16 times, and then we'll see what happens. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I got back to 3. Okay. So that means minus 16 doesn't do a single thing. So in modulo arithmetics, that means this whole thing here is not doing a single thing. So we just say that, aha. Is that okay? So modulo math is basically looking at numbers in a number circle. Okay? So for every operation, there's a mod 16 implicitly in this case. And you guys will be asking, but my cisp310 professor never told me this. There's a little implicit mod operation after every single addition or subtraction. But that's because that modulo operation does not need to be specified. It is just always there. Okay? Let me tell you, let me explain what I mean by that. Okay? So let's say you have unsigned. Okay? In fact, we'll use this representation, u int 16 underscore t. This is a variable x. Okay? All right. So let me explain first what u int 16 underscore t means. This is a type def that you can use if you pound include standard integer.h. Okay, so we'll use this later on in this class. I'm just giving you a preview. But all that means is it is an unsigned 16-bit integer. That's basically just all it means. Okay, it's guaranteed 16-bit. So when you say x plus, I don't know, 57, okay, it's really equivalent to x plus 57 and then a mod of what? What do you think it's modding with? It's really modding with 2 to the power of 16, the whole thing minus 1. It's always modding. But what you need to do is to think about it, okay? What if x is already the largest possible value that you can represent using 16 bits? Okay, think about that situation. If you just add 1 to x in that case, x is already the largest value you can represent as an unsigned integer. What happens when you add 1 to it? What does it become? It becomes 0, right? So the rest of the 57 is just adding 56 to it. That's the implicit mod operation at work. Is that making any sense? Because it is incapable of representing the actual value of 2 to the power of 16 minus 1 plus 57. So all it can do in that case is to give you back an answer of 56. Yep. Say again?
This is what overflow is then?
It is not considered overflow in C or C++. Your program does not break, no way to detect it unless you specify the logic, which is a problem because if you overflow an integer, there's no sign of overflowing an integer, except the math would be wrong. And that is why it is important to know how many bits you should be using for your integers. Because are you sure 16 bits is enough to represent the values that you need to represent? Okay, if you're not sure, you better calculate. You better analyze your program and say, okay, for this variable x, what is the largest value that we need to represent? Okay, and how many bits do I need to represent that value? Is 16-bit enough? If not, bump it up to uint 32_t, so you have 32 bits. If 32 bits is not enough, bump it up to 64 bits. But as a programmer, as a developer, you are responsible to understand how many bits you actually need to do because of this implicit mod operation that is always going to say, well, if you run out, we'll just kind of roll over and start all over again. What if you don't do this? Okay, what if you just say, well, the program works exactly the same way if I just say unsigned, okay? I'm just going to use this. What do you think would be some potential problems with that approach? Instead of explicitly saying how many bits x should be, you just say, well, unsigned, that's fine, it works. What do you think is a potential problem of that approach? Yes?
Well, you don't know, unless you have that spec with you, you don't know looking at it what the maximum value you can store in.
Because it depends on the compiler. Because how many bits unsigned is going to give you depends on the compiler. If you're using a compiler on a 32-bit system, which is kind of rare these days, but they still exist as virtual machines and also as Raspberry Pis, okay? Then unsigned is 32-bit because the processor built into the Raspberry Pi is innately a 32-bit processor. What if you're dealing with Arduino? Unsigned is 16-bit only. Now, granted, if you're using a modern operating system running on the PC, unsigned is 64-bit. So just because that program works on your desktop or on the power server doesn't mean that program will continue to work when you try to port it to a Raspberry Pi or an Arduino. Is that okay? But that is a problem because the fact that the program is working when you're doing it on the PC and now it's not working on a different platform means you have no idea why that is the case. It's exactly the same program, okay? It works here, it doesn't work over here. That is the reason why it is always a good idea to specify uint 32, 64, 16, because now it doesn't matter whether you're compiling the program on a 64-bit architecture, a Raspberry Pi, which is a 32-bit architecture, or the Arduino, which we kind of consider as a 16-bit architecture. It will still work the same. Now, is it going to be slower on an Arduino? Yes, but it's not going to be erroneous. Is that okay? So this is only important when you write programs that may be ported to different architectures, or you're using one architecture for testing and using another architecture for deployment. Do we kind of understand the concept of this whole idea? Okay, all right. So from our discussion over here, okay, 16 minus -2, and then the negation of 2, arithmetic negation of 2, ends up being the bitwise not of 2 plus 1. Okay, so let's formalize this, okay? So we're basically saying, give me a bit pattern, okay? X is a bit pattern. If you want to find out what is the binary representation of the arithmetic negation of x, it really is the same thing as bitwise not of x plus 1, which is called 2's complement. but that is why it works. So I just explained the math behind the scene of why 2's complement works. Well, let's try it on different values, because just because it works on 2 doesn't mean that it should work on other values, right? So we'll give it different examples. Let's go back to the number wheel, and I'll let you guys pick something for me to negate. So pick a particular bit pattern. It doesn't have to be the negative side or it has to be the positive side. Just pick one. Come on, somebody throw a dart at the numbers. Which one? I didn't catch it. -5. Okay, so we'll look at -5. So if you look at -5, it has a bit pattern of 1, 0, 1, 1. Okay, so let's work on that one. Okay, so x is -5, which is 1, 0, 1, 1 in base 2. So we'll try to figure out what is the arithmetic negation of that by doing 2's complement. So now we're basically saying -x, which is negative of 1, 0, 1, 1, should be the same as the bitwise not of 1, 0, 1, 1 plus 1. Is that part okay? Because according to my equation here, arithmetic negation is really the same thing as bitwise not plus 1. So are we still doing okay so far here? Okay, I'm just reapplying the equation that I have derived earlier. So now I look at this side and go like, okay, tell me what is the bitwise not of 1, 0, 1, 1? 0, 1, 0, 0, right? In base 2, and then we have to do a plus 1 over here. And what do you think is 0, 1, 0, 0 as a base 2 number plus 1? 0, 1, 0, 1. What does that represent? It represents 5. Oh, so it works, right? Because if we apply 2's complement to the binary representation of -5, it will give us the binary representation of 5. Does it work the opposite way? Okay, let's check it out. So what if x is 0, 1, 0, 1? So we want to work our way backwards, right? So now negation of x is the arithmetic negation of 0, 1, 0, 1. But since I claim that 2's complement is doing exactly the same thing as arithmetic negation, so now we say, well, we'll just take the bitwise not of 0, 1, 0, 1 and then add 1 to the result of the bitwise not. Okay, so what is the bitwise not of 0, 1, 0, 1? 1, 0, 1, 0 in base 2, and then we have to add 1 to it. And what is the result of that? 1, 0, 1, 1. Ooh, okay, so it seems to be reversible. It seems to work. What if I were to take the negation, arithmetic negation of 0? What should I end up with? 0. Okay, 0 is one of those strange values when you take the arithmetic negation of, it gets back to itself, right? Okay. Yep, the carry would be a 1, but the 4 bits would still be all zeros. Yep, but I will show it anyway. Like that. And then the bitwise not of 0, 0, 0, 0 is 1, 1, 1, 1. And then we add 1 to it. And that turns out to be just 0, 0, 0, 0. With a carry of 1 that we cannot see, right? So it does work. Okay, so this is how we take arithmetic negation, and the operation is called 2's complement. Now, this is another thing. Okay, it's not about the knowledge; it is about the acquisition of knowledge. When you hear the term 2's complement, what do you? Okay, some of you will naturally think of one thing. What do you think that is? The one thing that you will think of. If there's a 2's complement, there is probably a 1's complement, don't you think? Okay? So what is 1's complement? 1's complement is just bitwise not. The other name of bitwise not is 1's complement. The tilde symbol, the tilde operator in C is 1's complement. also known as bitwise knot. And that is why this is called 2's complement, because it's adding 1 to 1's complement. Is that okay so far? Okay. What time is it? Okay, we are almost out of time, so I think this is a good place to stop, but I do want to kind of go back to the notes a little bit because I want to show you what you can do over the weekend, because I'm not going to see you for 4 days, so there will be something that you probably want to read over these 4 days. So okay, so what we have done so far is we are getting into signed value representation. We are not quite entirely done with signed value representation, but we're pretty close to be done with signed value representation. The next topic is binary number comparison. Now that one is a little bit more complex compared to signed value representation, and there are certain equations and expressions that you kind of need to understand with this one. So you really want to read ahead of me over the weekend on binary number comparison. Okay? It does reuse many of the concepts that we have already talked about, but it also introduces some new concepts along the way. So that's going to be your new thing. And then for the lab tonight, we will be starting with subtraction and compare. Okay, so it's going to have a due date of next Thursday. So you have 1 week to work on it. So it's going to coincide with some of the discussions of comparison. Okay, but the negation part or signed value subtraction part, we already know. Yep.
When I checked earlier, the binary number comparison link did not work.
Oh, you mean the note doesn't work? Okay, I have to fix it. Okay, thank you. So this one, yep, it's still referring to the older server. Okay, well, let's see. That should do it. Yep. Yep, so it works now. Yep, I'll have to fix all the URLs too, but we'll start with this one. All right, so I'm gonna stop the recorder and then we'll head out to the lab.